This talk is about securing smart contracts with information flow. My name is Ethan Cecchetti, and this is joint work with Siqiu, Haobin, and Andrew Myers. All of us are at Cornell University. Securing smart contracts is a difficult but important task. There are a variety of tools that aim to do this in several different ways, that broadly speaking fit into two categories. The first is language-based solutions. These tools generally provide compositional security guarantees. So that means if we write two contracts in the same language that provide these compositional guarantees, not only are the contracts independently secure, but we can combine them into a larger application. We can compose them in a way that we know will retain that security. Unfortunately, the existing systems tend to assume that everything is written in the same language. And that means if this application needs to interact with another contract that is written in a different language or a piece of legacy code that doesn't necessarily provide the same guarantees, not only is this other piece of code potentially vulnerable, but those vulnerabilities might cause security problems within the original application itself when that code behaves in unexpected ways. The second approach are standalone static analysis tools. These tools can generally have no assumptions about what the other code that the contract might interact with is doing. So a contract that's checked with one of these tools can safely interact with an unchecked contract, some piece of legacy code, without having to worry about that code's vulnerabilities directly impacting the security of the original contract. Unfortunately, most of these systems consider only a single contract, and they provide non-compositional security guarantees. So that means while we can certainly check two different contracts, if we want to compose those contracts into a larger application, we have no way of knowing if that application will actually be secure as a whole product, or if it will simply be each of the individual contracts that end up behaving and interacting in unexpected ways. Our work aims to provide both types of security. We want compositional guarantees so we know that multiple contracts can interact safely with each other, but we also want the ability to have those applications interact with off-chain or legacy systems or code, simply contracts written in a different language, and make sure that they retain their security. To understand why having both of these together is so important, we need to look no further than a recent attack. In fact, less than a month ago, there was an attack in Ethereum where someone managed to exploit a reentrancy attack involving the interaction between two otherwise benign contracts and extracted $25 million worth of tokens in a variety of denominations from Ethereum's Uniswap exchange. So these problems are still very difficult to identify and can cost a lot of money when things go wrong. Our approach here is to treat this theft, these hacks, as integrity violations. Specifically, we want to prevent untrustworthy inputs from corrupting the trusted state within the system. So an attacker shouldn't be able to extract tokens that don't belong to them, as those tokens, the token balances should be considered trustworthy. To look into this a little bit more deeply, we're going to go through an example that in some ways is similar to the attack that happened a few weeks ago. Specifically, this is a vulnerable multi-contract bank. And what that means is a single bank application that's split across two different contracts. Each of these contracts contains some amount of money, and the combined money between the two are the total assets of the bank. Also, each of the contracts independently holds on to the entire balance sheet of the bank. So it knows that, say, Alice's account has $50 and Bob's account has $20, and each contract has its own copy of this, but those two copies need to remain in sync because they both represent the same thing. They both represent the total account balances at the bank. Also, both contracts are running exactly the same code. We're not going to worry about most of the code, but we are going to take a deeper look at a specific part of the code. So if Bob comes in and says he wants to withdraw some money, what does the bank do? Well, Bob has requested to the first contract that he would like to withdraw $10. So the first thing that the bank contract does is it checks its local copy of the balance sheet. Much more efficient than, say, going to another contract, and it sees that Bob's account has $20 in it. Bob's asking to withdraw $10. This is fine. So it updates its local copy of the balance sheet and reduces Bob's account balance to $10 and sends Bob his $10. Because of how Ethereum and other smart contract systems work, when the bank sends Bob this $10, it has to wait for him to return. So what Bob should do, and what the bank hopes he'll do, is pocket the money and return, giving the bank the ability to continue with its execution, at which point it's going to notify the other contract. The first contract will notify the second one to update Bob's balance that he's withdrawn $10, and now the transaction can complete, and the bank remains in a consistent state, and Bob has taken his $10. This is what's supposed to happen. This is how these two contracts are supposed to be able to cooperate with each other. And everything works fine if Bob does what they expect him to. Unfortunately, Bob might not be so nice. Bob might be trying to steal money from the system. And if he analyzes this code very, very carefully, he's going to come up with an idea. He's going to start the same way he did before. He's going to ask the first contract to withdraw $10. And it's going to perform the same operations. It sees he has $10. It reduces his balance to 0. It sends him his $10. But now, while the first contract is waiting in step 3 for Bob to return from this send, Bob isn't just going to pocket the money and return. Bob is going to say, hey, contract number 2, please send me $10. I would like to withdraw money. Well, contract number 2 is running exactly the same code as contract 1, so we run through the same steps. It checks Bob's balance in its local copy of the balance sheet. Well, that hasn't been updated yet, so that still says that Bob has $10. So it's going to decrease that down to 0, and then it's going to send Bob his $10. Bob just withdrew $20 when he only had $10 in his account. He's overdrawn his account balance, and he did this by violating trust that the bank had implicitly placed in Bob. The bank implicitly trusted Bob to return when it sent him $10 instead of making another call. But Bob didn't do that. He made this reentrant call into the other bank contract. Even though it was into a different contract, it was still a reentrant call into the same application and violated the bank's trust. So we would like to be able to identify the places where the bank is implicitly trusting its users to do something like this and be able to avoid this kind of vulnerability. And the way that we're going to identify and eliminate these bugs is using something called information flow control. And information flow control, the basic idea is that we want to label data and computation to track how different inputs affect different outputs. So we might have, say, trusted and untrusted data, and the trusted data might be allowed to influence the untrusted data, but not vice versa. We don't want some untrusted input to be able to change how the bank operates or to be able to cause extra money to move somewhere. One really nice property about IFC is that we can check it with a type system. By checking it with a type system, we're able to ensure that it gives us composable security guarantees. So we've sort of had the first half of this style of security guarantee we want is that we're going to be able to compose contracts together and enforce security across the entire application. Now let's see how we can use IFC on our bank example. We're going to start with just standard off-the-shelf information flow control, nothing new. And we need to tag all of our data and code with a trust level. So maybe the data at the bank is marked as trusted and the money is marked as trusted, right? The balance sheets and the money are important that they stay correct and that they not go anywhere they shouldn't. So we'll mark those as trusted. The withdraw code needs to modify the balance sheets and needs to decide when money gets sent. So that code better also be trusted because it's doing some kind of important things. Bob, however, might be trying to attack the system. So we're going to mark Bob as untrusted because we don't know if he's trying to do anything untoward, and so we want to make sure that we don't let him do things he's not supposed to. But now, if we actually try to use this contract and have Bob withdraw some money, we're going to run into a problem. There's a standard rule in information flow that prevents untrusted callers from calling trusted code. And this is to stop an untrusted piece of code or an untrusted user from influencing what trusted actions happen when. So this means when Bob tries to make his first withdraw call to the first bank contract, totally above board, not an attack, this is exactly the same as standard normal operation, we sort of have two options here. If we mark this withdraw function as trusted, the way we have here, then this simple IFC rule is going to block this call and prevent Bob from withdrawing any money in the first place. This isn't an attack. This is just Bob trying to get his money out of the bank legitimately. So that's not good. We don't want to block that. We want to allow Bob to call withdraw. But if Bob's not trusted, the way to let Bob call withdraw is to mark withdraw as untrusted. So now the call can go through. But if we mark withdraw as untrusted, then that code can't modify trusted data. It can't modify the account balances. It can't send money. It's locked out of performing the very operations it's supposed to perform. And so the code doesn't even work. So neither of these options are valid. Neither of them actually allow the bank to function properly. And indeed, standard off-the-shelf information flow doesn't work here. It completely destroys the entire functionality. I guess the bank's secure, but it's because it doesn't work. So we're going to have to change information flow control a little bit to get the results we want. And the first thing we're going to do is we're going to create something called a trusted entry point. This is a technique that's been used in other systems as well. And the basic idea is to allow untrusted users to call trusted code, but only at very specific locations. And so we can now mark the withdraw operation as trusted, the way that we did before, so that it can actually perform the operations it needs. And we specify that this is an entry point. So we're going to allow Bob to call withdraw, even though withdraw is trusted and Bob is not. And so he can still call it and it can still send him his money. So we have the basic functionality of the bank back. But wait a second. In the process of recreating this functionality, the original reentry attack works again. Bob can still make that reentrant call into the second bank contract, and it will be allowed because withdraw is a trusted entry point. So it seems like we've gained nothing. It seems like we've come all this way for no benefit. But don't worry, not all hope is lost. We've actually gained a lot here. These trusted entry points have specifically identified critical sections in the code. They've identified what code we have to worry about and what code we have to be careful with. And more than that, they allow us to actually formally define what we mean by reentrancy. I've been using this term throughout the entire talk, but I never really told you what it meant. And we're able to use this sort of trusted, untrusted entry point thing to actually define it. And specifically, the way we define reentrancy or reentrant execution is an execution stack where we have two trusted operations separated by an untrusted one. So for example, if we have withdraw that sent money to Bob, and without returning, Bob called withdraw again, we have two trusted withdraw operations on the stack and an untrusted Bob operation sitting between them. And so this would be a reentrant execution. However, if Bob's actually behaving as the bank expects him to, and he calls withdraw and doesn't do this attack, and withdraw might call a synchronization operation on the second contract that's also trusted, but that's fine. We have two trusted operations next to each other, so this is non-reentrant. One of the main reasons we want to make this distinction is because reentrancy is notoriously difficult to reason about. And so we want to make sure that programmers only have to reason about non-reentrant executions when they're trying to figure out if their code works properly and if it's secure. And in particular, we want to guarantee a notion against reentrancy vulnerabilities that says intuitively that reentrancy doesn't create bugs. Now, what does it mean to create bugs? Well, formally what we have here is that we want to say that reentrancy doesn't create new behaviors in the contract. There's nothing that you can make the contract do using a reentrant call that you couldn't make it do using non-reentrant executions. Now, our vulnerable bank is not secure according to this definition. Because Bob was able to overdraw his account balance, he could take out twice as much money as he was supposed to using that reentrant call. But if he only stuck to non-reentrant calls, he never would have been able to overdraw his balance. He could only take out $10 from when his account had $10 in it. So this is nice. We've been able to actually define reentrancy and define a clean notion of security here using this trusted and untrusted dichotomy. But how do we enforce security? Well, we enforce it using a locking mechanism. Specifically, we want to lock integrity levels. And we do that when we use an entry point. So if we have this trusted and untrusted levels, and Bob, say, calls withdraw and enters into an entry point, that entry point is going to lock the trusted level that it sort of grants this extra integrity and locks it in the process. And once that integrity is locked, we want to prohibit re-granting it. So you shouldn't be able to use another entry point that gives the same integrity that was already locked. You can still do things that, say, reduce integrity. So the bank can send Bob money. And in fact, this first withdraw and the send operation are all that are needed for the honest withdrawal. When Bob wasn't trying to attack the bank, this is all that was needed, and so that operation works just fine. However, when Bob's trying to attack the bank, from here, he creates another withdraw operation that tries to go into one of these trusted entry points again, but here, the trust is already locked, and so our locking mechanism is going to prohibit this call from happening, and it's going to prevent the attack entirely. There are a couple of different ways of actually enforcing these locks. We can do it statically or dynamically. If we do it statically, we can use the type system to actually track what's locked when and whether or not a call is safe or if it's potentially going to violate one of these locks. That has a really nice property that there are no runtime costs whatsoever. Everything's checked by the compiler, and if it compiles, we know the code is safe. Unfortunately, it assumes all of the code it's interacting with is well behaved. It assumes that that code is also not going to ignore these locks. And that violates one of our core security tenets that we had at the beginning, that we should be able to interact with arbitrary code, including code that doesn't maintain the same security guarantees we do. We can also handle the locks dynamically at runtime. This has a potentially high runtime cost because we have to actually store what locks are what integrity is currently locked and check these locks every time we hit an entry point, but it works with arbitrary code. Because if I lock my own integrity, I can call somebody else, and I know that if they misbehave, if they do something I'm not expecting, I'll be able to detect that through the locking mechanism and stop the transaction from happening. We'd like to get both of the good parts of this with neither of the bad parts, and so we're actually going to use both. By default, we're going to use the static locks tracked by the type system. And this disallows, and in order to do this safely, we're actually going to completely disallow calls to code that might behave improperly, to code we don't trust. So this is very restrictive, but it's safe. If a programmer wants to call some other arbitrary code, they can request a dynamic lock. When they request a dynamic lock, the type system releases the lock statically and allows that call to go through, knowing that it will be dynamically checked to make sure nothing bad happens. So what have we done here? We've provided compositional security guarantees, and we've done it in a way that allows for safe interaction with legacy or unknown code. And we have a couple of other pieces in progress. We're in the process of building a compiler for a language that enforces all of these. We're working on more permissive rules. Some of you who are familiar with reentrancy may have noticed there was a slightly easier way to fix that contract, that bank, than all of this fancy locking mechanism. So we're working on being able to recognize that when we can and still use the locks when we need to. And also we're working on proofs of security. And with that, I would like to thank you.